Of the four basic types of transformations, the only one we really haven't seen in detail is a dilation. We've talked about translations, rotations, and reflections, and the final basic type of transformation is something that we call a dilation. And what this video is going to do is it's going to take us through the basic definitions and notation and terminology surrounding dilations, and then move dilations from a basic blank plane onto a coordinate plane so we can see how it interacts with some familiar ideas like coordinates on a coordinate plane and distance on a coordinate plane. So first, the definition of a dilation is any transformation that enlarges or reduces the original figure proportionally. So one of the ways we can think about that is if we have a triangle that we made a copy of and moved it down and to the left. Well, at the moment, this is just a translation. The original size of the figure is still the same, and all we've done is movement. But if instead, as a part of that motion, the figure increased in size, well, then it becomes a dilation, and in this case, a dilation that enlarges the figure. If we were to check side lengths of the original triangle to the side lengths of the image triangle, we will find that all of the side lengths are proportional. Similarly, we can make another copy of this triangle figure and have it shrink as a part of that motion. In this case, it is a dilation that reduces the original figure proportionally. And much like similar figures, when we talk about the extent to which an original image is enlarged or reduced as a part of a transformation of dilation, we call it a scale factor. And the scale factor of dilation is the ratio of the size of the image to the original figure. As in similar figures, we calculate it as the ratio of segment lengths. So go ahead, pause the video, copy down the definition of dilation as well as the definition of scale factor of dilation. You can go ahead and draw those two examples of dilations, enlargement, and reduction if you want to too, but pause the video, copy down those definitions, come back when you are ready to move on. So when we're talking about the scale factor of dilation, when we saw scale factors in similar figures, we could envision the scale factor in either way. A scale factor going from the smaller image to the larger image, or from the larger figure to the smaller figure. However, when it comes to dilation, it must be the same way every time. The order of the scale factor matters. It is always calculated as the size of the image to the size of the original, never the reverse. And in part, this is because we want our scale factor to represent something intuitive about a dilation. If we have a scale factor that's bigger than 1, say a scale factor of 3, we are going to naturally interpret that as the image is 3 times as large as the original. Similarly, if we have a scale factor of 1/10, we are going to naturally think about that as the image being 1/10 the size of the original. So scale factors are always image to original and never the reverse. Go ahead, pause the video, and copy this down. This is an incredibly important part of what scale factors are and how we calculate it. Come back when you're ready to move on to the last series of definitions and then go on to a coordinate plane. So again, when we're talking about a dilation that makes the image smaller than the original is called a reduction, and a dilation that makes the image larger than the original is called an enlargement. Another thing that we can talk about with a dilation is something called the center of dilation. When we're talking about dilations on a plane, whether it is a coordinate plane or a blank plane, they are always performed relative to a fixed point in space. You can think about it in some way as the center of a circle, as that circle is expanding outwards from its center, getting bigger and bigger and bigger if the center never changes. We call this point the center of dilation. When we first started talking about similar figures and you did the exploration in GeoGebra to see about the reduction or enlargement of similar figures, it asked you in GeoGebra to choose a center of dilation, because when we are actually performing the transformation of a dilation, it's not just enlargement, it's enlargement in a direction and with a particular scale. Similar to the idea that when you reflect across a line. When you rotate around a fixed point called the center. And when you translate, you have some sort of instructions for how to translate. Another way we can think of the center of dilation is that the light source that projects a movie onto a screen in a cinema or a movie theater or just on a screen that you have, that is the center of dilation for the original film and for the projected image. So go ahead, pause the video, copy down the terminology for a center of dilation, as well as the image that's down here on the left that has a center of dilation. You can find the center of dilation by following along from point to corresponding point in image, to original, and back to that point. Wherever those lines intersect, that is the center of dilation. So go ahead, pause the video, come back when you are ready to move on. One last piece we have to talk about as it relates to the terminology and notation around dilations is how we represent it. We represent it using subscript. The basic notation for dilations is D subscript K, comma P. K is the scale factor, P is the center of dilation. Now, if we have it on just a regular old coordinate or regular old plane that does not have coordinates on it, then our center of dilation is going to be whatever we name the point. So if it's P, that's great. If it's A, it is D subscript K, comma A. And the scale factor, again, is the ratio of the image to the original. So we know whether this dilation expands or shrinks images. So go ahead, pause the video, copy down this notation. Then we're going to move on to some coordinate planes, and after a few examples, ask you to do some dilations on your own. So let's go onto a coordinate plane and see what this means when we're specifically performing these kinds of transformation on a coordinate plane. So here we have a triangle in the first quadrant, and we are being asked to perform the dilation D2, O. And in this case, and in most cases when we are talking about dilations, we are always going to do dilations from the point of view of O, which is the origin. We can have the dilation center at any point on the coordinate plane that we like, but particularly now when we are first talking about it, we're going to have it center at the origin. So there are a few different ways that we could think about this. The first is starting at the origin. Let's add a dot at the origin there. We can trace to each of the 3 points of this triangle and make the distance from the origin to the point twice as big. So to get from the origin to the far left point of the triangle, we go up 4 and over 1. Well, the dilation has a scale factor of 2, so we do it again, and our next point is there. Another way we could talk about it is recognize that the point that we just transformed was originally 1, 4, and notice that because we're centered at the origin, the image point is now twice as far at 2, 8. The x is twice as big because we followed that same direction and magnitude twice, and the y coordinate is twice as big. Similarly, if we were looking at dilation to the point up in the top right, over 4 and up over 5 and up 4 means that we are going to do the same thing to get to the new image point. Keeping track of coordinates, this image is, or the original is at 5, 4. The image is at 10, 8. Again, dilation with a factor of 2, multiply the coordinates by 2. Do the same thing with the third coordinate, over 4, up 1, over 4, up 1. To our third point, the original was at 4, 1. The new one is at 8, 2. So now we just take our 3 points and we connect them as we did before. And now we have our transformed dilation, a figure that is twice as large as the original, centered at the origin. Let's take another look at this, and this time we'll move a little bit faster. Again, we still have a transformation that is centered at the origin. But now we want the scale factor of dilation to be 1/2. So let's take a look at that from a coordinate point of view. The coordinate for the point up in the upper left-hand corner here is 2, 8. Multiply both coordinates by 1/2, and our new point should be 1, 4. Go to this point over here. The coordinates for that point are 1, 2, 3, 4, 5, 6, 7, 8. 8. A dilation of 1/2. Divide both by 2, and our new point is here at 4, 4. Now, we're going to go down to the point where our image just came from, the original point 4, 4. Again, multiply both by 1/2 to get 2, 2 as our new image point. And finally, over in the bottom right corner, which was originally 6,4. Divide both by 2, and now you get 3,2 as the image. So our new shrunken or reduced figure now looks like that. And we can double check that by drawing those arrows out from the origin. 0 through the image up to the original point. Great. 0 through the image straight to the original point. Great. 0 through the image straight up to the original point. And finally on the last one there too. We can always double check on a coordinate plane by drawing lines that connect center of dilation with corresponding parts of the original and corresponding parts of the image. One last type of dilation before you have a chance to do this on your own. Dilations can also have negative scale factors. What that means is that it reflects the image back to the opposite side of the center of dilation. And it has the same properties that we would want it to as it relates to coordinates. So the original coordinates are 1, 1. New coordinate is -1, -1. Original coordinate is 5, 1. New coordinate is -5, -1, which is right there as it turns out. And then original coordinate 5, 4. New coordinate -5, -4. That's -5, -5. So it should be that one there. And then we just connect all of our vertices. Again, as one last double check, from original through the center of dilation, original through the center of dilation, all of these arrows going from one to the next all go through the center of dilation, which means we have plotted it correctly. So original image when we have a negative scale factor. So go ahead and take this image right here. You're going to scale it under the following two dilations, one in red and one in green on the screen. Dilation of -3/2 relative to the origin and 3 relative to the origin. Pause the video, go ahead, do this in your notebook, and then come back when you are ready to see the dilations and review the terminology in the video. So it's really helpful when we're doing these to know what our original points are. So our original points are 3, 3, -3, 3, and 0, -3. Well, if we're looking at our dilation as -3/2, 0, to multiply, or -3/2 out of the origin, if you multiply 3 and 3 in our first coordinate over here by -3/2, we get -9/2, -9/2. So that's going to go all the way over here to -4.5, -4.5, which is basically right there. -3, 3 then goes from -3, 3 multiplied both by -3/2 to 9/2 and -9/2, which is right on top of the -3 there. And then 0, -3, 0 times -3/2 is still 0. -3 times -3/2 is 9/2. So our new figure, none of them having coordinates that exist on the lattice grid of integer coordinates, now looks like that. If you wanted to, you could draw arrows through the center of dilation at the origin from the original to the image, and you'll find that they all go through 0, 0. Now, if we're going to look at it from the point of view of dilating it by 3 over the origin, then 3, 3 multiplied by 3 is 9, 9. 6, 6, 9, 9. -3, 3 multiplied by 3 is -9, 9. And 0, -3 multiplied by 3 is 0, -9. And then we just connect all of our points there. So it expands it around the origin and gets much larger. So those are the basic ideas of dilation. Dilation, again, is just a transformation that enlarges or reduces a figure. It can happen in an enlargement or a reduction. We talk about it as scale factors, and we always have this point, which in these cases has been the origin, that is called the center of dilation.